Thank you, Giovanni. Good morning, everybody. Actually, it's probably evening for you guys. I changed a little bit the talk, and I will be talking about MemComputing still, but for applications to the third wave of artificial intelligence. So we'll tell you what this means. And this is work that is, sorry, I'm trying to get. So this is work that is funded by the Center for Magnetic Recording Research and the Department of Energy, DARPA, and National Science Foundation. I also have a company that actually released the software as a service, and if you are interested, you can actually go and try it for free to check, if you want to reproduce some of the things I will be discussing today. So what are the waves of artificial intelligence? So DARPA classifies them according to three waves. So the first one is traditional programming, which is our computers, logic-based programming, rule-based programming. The second wave is related to neural networks, deep learning, what we use nowadays, and employs a supervised learning. I will tell you in a moment what that means. And the third wave is defined by DARPA as machines that can generalize very efficiently from a very small set of data so that they can adapt in the context. So this is called context adaptation, in the context in which they operate and learn without much supervision. Now, to realize this third wave, so as I said, we have the first and the second, in fact, they're well developed. But to realize the third one, we need to transition from supervised learning to efficient unsupervised learning, which is not a trivial thing. So as an example of this, let me show you a neural network, which is very famous, which is a restricted Boltzmann machine, but the type of ideas I will show you actually apply to any type of neural network. And we chose this one also because it has a universal representability of discrete probability distributions, which means that they can represent, if you can train them efficiently, they can represent any probability distribution. And these neural networks have a probability distribution, which is a Gibbs distribution, a Boltzmann distribution, that's the name, with an energy which is like a spin glass, where you have interactions between a visible set of nodes or neurons, VI, and a set of nodes, hidden nodes that actually have to learn features. And they interact through some weights, and you have biases on these nodes, which are like local fields. So this is like a spin glass for those of you actually who know this. Now, if you want to do unsupervised learning, what do? You just plug in data, right? And you hope that the whole network will learn the features of this data. This is an extremely challenging problem. In fact, it's not even more difficult than what we actually use nowadays in our in deep networks. And in fact, to simplify things, what we do is we add an output layer, and then we a backpropagation in a supervised learning fashion to actually fine-tune the weights, so that in this way we actually learn in a supervised way the features that we want to learn. Now, this is still challenging. The most important thing is that it's difficult to use to generalize and to use it for contextual adaptation. So it's not a trivial, it's not deployable in what we call the third wave of artificial intelligence. Now, why is it so difficult? Why is it difficult to train these neural networks? And this is true not just for restricted Boltzmann machines, but for any Boltzmann machine, neural network. Now, the reason is that when you actually have a neural network, you define a multidimensional phase space, which is corrugated as a highly non-convex landscape. And what you want essentially is to find the ground state in this high-dimensional non-convex landscape. So it's like finding a needle in a haystack. It's not a trivial thing. In fact, if you go into details, when you actually want to, for example, train a restricted Boltzmann machine, you need to find the minimum of this energy, the ground state of this energy. And you typically do it by using a gradient descent on the weights, where you have two terms. One is called the data term, which for an RBM is actually easy to do, but you also have what we call a model term, where you actually try to model the probability distribution, and this is really hard to do. In fact, this problem, for example, this energy is minimizing that energy is what in computer science is called a quadratic unconstrained binary optimization, which is it's essentially a max set. It's an NP-hard problem, so it's very tough to solve. So you need a completely new ways of computing if you want to solve this type of problems, and that's where this paradigm comes in, that we call MemComputing, computing with any memory. But by memory, we mean time non-locality, non-necessary storage. So to introduce this computing paradigm, let me remind you how we actually compute nowadays. We actually use the Turing paradigm, which is essentially a mapping between a finite string of symbols into a finite string of symbols, and the transition function between these sets of states of symbols is an algorithm, right? So that's how we actually compute most of the problems we have. So what we want to do is actually use physics to compute, similar to the talk previous talk, or quantum computing, for example. And physics, it's incredibly powerful. For example, if I have here the water flowing down a hill, now the water, actually what it does is simply calculates, if you think about it, it calculates all the paths they are available to it without any effort, right? So a physical system, in fact, has no choice. If you design a physical system, in this case, if you have water flowing down a hill, well, it has no choice. It has, in physics, we know it has to render an action stationary, and there is no choice for the physical system. It has to do it. It has to do whatever it has to do because it's in its nature. And the other thing is that a physical system has no knowledge about the difficulty of a problem. So this one, for example, would be very tough to simulate if you take into account all the possible corrugations, defects, interactions, and so forth. And yet, water does it effortlessly without actually warning. So a physical system, if you can design a physical system that actually solves a tough problem, well, it has to do it. There is no other choice. And it doesn't care whether the problem is classified hard, easy, or according to some other classification that we use in mathematics. So that's the starting point. And so that's what we want to do. But we want to actually keep the input and the output digital so that we don't have issues with precision, and we can actually scale these machines. And digital means that we can read and write with an error that is independent of the size of the problem or the machine that we are using. And then we want this to be actually easy to fabricate with the current technology. We don't want to go the route of quantum computing, which would add additional problems. Now, as I said, it's fundamental that the input and the output are a finite string of symbols. We will choose zeros and ones, which is typical. And the reason is because, again, if I have here a real number, here also a real number in the input and output, then I need, in principle, an infinite precision to actually, get those numbers, and so you have issues with scalability. But if this is an integer, a set of integers in both input and output, then you can read and write with an error that is independent of the size of the problem, which is, by the way, what we do in our current computers, right? We use transistors, which are physical systems, but we can assign a 0 and a 1 according to a very high or low current with a threshold. And we will use physics to map these integers into integers. And in particular, we will take advantage of the physics of time non-locality memory to do this. So MemComputing machines are essentially, apart from an input and an output and a control unit that tells the machine what type of program to execute, we envision that the entire computation is done by units we call mem processors or computational memory, where both the processing and the storing of information is done. And again, by MEM processors, we don't mean only long-term memory, but we also intend any type of time non-locality. Now, this is, again, much different, as you know, from the von Neumann architecture, where you separate the memory from the CPU. Now, as a practical way of realizing this, let me show you how we go about. So suppose you want to solve a Boolean problem that is written this way, where you have a set of clauses that relate to variables, let's say x1 and y1, and these clauses are related by logical ends. And as the previous speaker said, you can transform this actually into a Boolean circuit, the circuit beneath, for example, which is a collection of OR gates, multi-terminal OR gates. And you can have NOT gates as well, and then you connect all the variables and their negations, so the literals. Now, if you know the answer, of course, you can just plug in the numbers and you get the you check whether that actually satisfies this Boolean formula. But what we want is actually the reverse, which also the previous speaker mentioned. So we want to actually set the formula to satisfied, right? And we want the system to self-organize, find itself the solution of this problem. So this is where the difficulty comes in, right? We want to invert these one-way functions. So what we will do is we take any combinatorial optimization problem, which can be written as a Boolean circuit. It's not even unique. In fact, some circuit representations may be more convenient, both in hardware and software. And then instead of using the standard gates, which are unidirectional, we use our gates, which we call self-organizing logic gates, which are terminal agnostic. So here is, for example, an AND gate where you have the truth table on the far left. And these are unidirectional, which means that you give an input and you get an output. There is nothing else you can do. So this thing goes in one direction. The logical topology is unidirectional. But suppose now that you replace inside this gate, so you expand the space of these inputs into a much bigger phase space that contains also internal memory variables, variables that give time non-locality to the system. So you transform the problem into a physics problem. Then you can design these gates so that they actually work in both directions, which means that you can design them as physical systems that have only, in this case, four steady states, for equilibrium points, the ones that satisfy the logical proposition of this particular gate, which is an AND. So that if I actually get on top, on top of 1, 1, then at the bottom I will get 1. But the same, if I give at the bottom 1, I will also get at the top 1, 1. So I always satisfy the logical proposition. And if I give, for example, at the bottom 0, I will have 3 steady states, 3 possibilities. Which one will be reached? It depends on the initial conditions, because now this is a physical system. We call these self-organizing logic gates, and again, they're designed to satisfy logical propositions, in this case 4, or better, we map those 4 logical states into 4 equilibrium points of this dynamical system, and we design them to satisfy the propositions irrespective of where the signal comes in. And when you put them together, then you let them self-organize by giving, some input and reading the output some terminals. So you let these ones to collectively, in a massively parallel way, collectively, self-organize to find the solution. So in practice, what we have is we actually put what we call dynamic correction modules, which are objects, active objects. They read let's say we are representing the circuit, the electrical circuits, and this the top one is 1, the other one is 0, this one is 1. So this is not satisfying the logical table. So this gate on the top right will actually read the other 2 voltages and will inject current at from 0 to 1 and satisfies the logical position of the gate. The bottom one will also do the same, and in this case, it realizes it's not in the consistent logical proposition. It takes out current and it actually goes from 1 to 0 so that it satisfies the other proposition, and so forth. So they will actually try to satisfy each other. I mean, they're locally their logical proposition. Which one wins, again, it depends on the initial condition of the physical system that represents this. And you can build this in many ways. You can use resistive memories, and these, for example, can be done with spintronic devices, like the ones that were discussed before, or you can do in CMOS, fully CMOS, so you can actually emulate resistive memories using transistors. The important point is that you can design any type of gate, whether an OR, an AND, XOR, whatever, using this type of idea. So essentially, you can design any type of gate to operate as a terminal agnostic gate. So if you write down all the equations of these circuits, in this case an electrical circuit, well, these are simply differential equations, nonlinear differential equations, whose variables are the currents, the voltages, and internal memory states. So essentially, these are ordinary differential equations of the full circuit, which you write down using Kirchhoff's laws. And these are ordinary differential equations, which actually can be efficiently simulated in software, right, on our computer. So this is the incredible thing. And the difference with the quantum computers that cannot be simulated efficiently on our traditional computers, because the Hilbert space explodes exponentially in that case. So these are actually nonlinear dynamical systems that follow ordinary differential equations in a phase space which grows linearly with the number of dynamical variables. So that's it's fundamentally different. And so here is where the hard work comes in. We had to prove that if you make points of this dynamical system equal to the logically consistent states of the gates, then you have to eliminate periodic orbits and chaos. So you can prove, in fact, you can design these systems so that they don't have periodic orbits and chaos. Of course, if you can also represent the logical states with the periodic orbits, in that case, you will have to eliminate equilibrium points and chaos. And I don't know how you would actually represent chaotic behavior with chaotic behavior, logical consistent state. So either equilibrium points or periodic orbits, and we chose equilibrium points. So you can actually demonstrate this. The demonstrations are quite long, so I refer to the papers. And so how do you actually solve a problem, a combinatorial optimization problem using these machines, MemComputing machines? So you select the problem, for example, traveling salesman or some other problem. You convert in binary representation, and this is actually not unique. And the important thing is you replace the standard unidirectional gates with our self-organizing logic gates. And either you build these devices in hardware, or, and that's what I will show you, you can simulate their dynamics in software, which is already incredible because, again, you cannot do this with quantum computers. So for quantum computers to have any advantage, you have to build them. And then you read the solution, the appropriate terminals. So here's a recent example. We just published it, I believe, last week. So it's an NP-complete problem. It's the 3 set where you have all gates are have 3 literals, variables are their negations. And if you write down the equations, so you can find the equations in this paper, but these are the equations for the voltages and internal memory variables. And these are ordinary differential equations of the gates that we put together. Now you can prove analytically in the continuous dynamics, this is important, using topological field theory, that in fact these dynamical systems will find the solution with a time that scales sublinear, linear or sublinear with the number of variables. Now this is not true in discrete time, which is what I will show you, where you actually discretize these equations with any numerical method. So the only thing we can say about this is that in continuous time this thing will be polynomially scaling. So we did not prove NP equal to P, because to prove that statement you would have to prove that also in the discrete time where 2 machines operate, then this thing is also true, and we didn't. However, as I will show you, even the numerical simulations are incredibly powerful. Here we chose, remember that when you actually look at NP-complete or NP-hard problems, you have to choose really the tough ones. Otherwise, you can always find easy ones. So we chose really tough instances, which are called Barthel, and are hard satisfiable instances that are used also in competitions for this. So if you're interested, you can take a look at this. And here is an example. So in the main panel, we have the simulations of our MemComputing machines for different iterations of clauses to variable. The most difficult ones are at 4.3, and they scale as cubic and most variables. We push this to millions of variables, by the way. And on top, you have two state-of-the-art algorithms like message passing and WhatsApp. And as you can see, they actually explode exponentially pretty fast. I mean, a few hundred variables. Remember, this is a log linear space, and this is log. And in fact, the largest case here that we did for each instance, it took about 15 hours. And if you try to extrapolate this for the other two state-of-the-art algorithms, it would take more than the age of the universe. Now, for example, this is true also for other problems that we looked at. One is MaxSat, for example, where you're looking for the maximum number of satisfiable clauses in a set. And here we actually gave our code to the Supercomputer Center, and they did it on tough instances taken from this competition. And again, two winners of that competition explode exponentially in time versus number of variables, while ours actually scales linearly in this case. And in fact, if you extrapolate the other two, it would take more than the age of the universe again for them, while the Supercomputer Center did per instance in about 2 hours. So this is not an accident. We have now done tons of tests from all optimization problems like random to MaxSat, MaxCat, and so forth. This is again done by the Supercomputer Center as a third party, unimpeachable third party. We extended this to integer linear programming where you have algebraic relations and not Boolean relations. And we solved the problems that were not solved in decades. And I will show you in a moment how to apply this to deep learning, to do unsupervised learning. We did this also on ground state of Ising spin glasses, and the company is working with several other companies to solve problems. And these are more than 100,000 instances, so it's not a fluke. So to tell you how to apply this efficiently to do unsupervised learning, let's start first on supervised learning. And as I told you, suppose you have a restricted Boltzmann machine and you want to train it, then you have to evaluate these terms, which are averages over probability distributions. So the first one is easy for an RBM, a restricted Boltzmann machine, but the second one is really tough, and it's an NP-hard problem. Why it's tough? Because again, if you use standard methods like Gibbs sampling, you have a hard time, find the mode of this probability distribution, which is an NP-hard problem. And instead, we can do this very efficiently, as I showed you with MemComputing. So that's what we did. So that was our first test. And we compare with the standard approaches like Gibbs sampling and for mixed data set. And as you can see, it's difficult for them for Gibbs sampling to train these machines. D-Wave actually used its annealer actually in hardware, right, to do it, and it accelerates significantly the training, but it is in hardware. It has to do it in hardware, and we did this actually on a laptop, and we get the same acceleration as the quantum D-Wave, but a better quality, in fact, less noise. Now, this we actually compare with state-of-the-art algorithms for supervised learning, and we are consistently better. In fact, we get error reductions on more than 20% compared to state-of-the-art algorithms. And if you're interested, you can look at the paper. So this is supervised learning. As I said, if you want to realize the third wave of artificial intelligence, you have to do unsupervised learning. Which means that you don't have any output on which you can actually train the machine. So it has to do it on its own. So here is an example. Again, we take the mode samples, as I said, from MemComputing, because we can do that very efficiently. And here is the KL divergence, which quantifies how different is the distribution that is obtained by the machine compared to the data distribution. And of course, when this goes to 0, then you have matched the data distribution. Now, this is considered impossible to do. In fact, the Gibbs sampling can even diverges at a certain point. The more you train, and the worse it becomes. But here is in red, you see the MemComputing approach. And in fact, we can reach essentially 0 KL divergence. So we can learn efficiently the distribution, the data distribution of the data set, which is considered impossible. And here is an example of this. On the left, you have the Gibbs sampling that struggles precisely to find the modes of the distribution, and on the right you have MemComputing, which is instead always finding the modes or close to the modes. We can sample the mode efficiently, and it goes essentially to the data distribution, matches the data distribution. Now, we tested this with many data sets. We always consistently do better than any other approach in all data sets. If you're interested, you can look up the paper at the bottom. So we extended this, by the way, on also to deep networks, not just RBMs, and we have similar results. So let me conclude. We have introduced a new class of machines we call MemComputing machines, where memory means time and locality, that can compute efficiently non-convex complex problems. And the practical realization of these machines can be done using what we call self-organizing circuits, which are terminal agnostic circuits or terminal agnostic gates. And you can build this in hardware, either with resistive memory, spintronics, or CMOS, or incredibly, you can actually simulate these things in software. These are, by the way, deterministic differential equations, so you don't even have noise. The only noise we have in software is the numerical noise, not the external noise. We could put it, but we don't need it. So we've been working a lot on machine learning. I showed several results of that. Optimization, I also showed that. We're now working on quantum Hamiltonians to find the spectrum of quantum Hamiltonians, which is another optimization problem. And if you want to do real-time computing, of course, you need to do hardware, because the software, as much as nice, I mean, it is better than other algorithms, but it's still time-consuming to do numerical simulations. You have to discretize time. So these are the students who worked hard on these projects, Sean, Haik, Rudy, and Yuan Han. The funding agencies are below, and thank you very much for your attention. I'll take any questions from here.